Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the output voltage. A model can be developed for the various processes that occur in a fuel cell to predict the performance. From the thermodynamic analysis, we found the theoretical voltage created by the process and the EMF from the Gibbs function. At both electrodes, there are activation losses that lower the voltage and a leak current that does not go through the cell. The electrolyte or members of the cell has an ohmic resistance to the ion transfer and thus also produces a loss. Finally, at high currents, there is a significant cell concentration loss that depletes one electrode for reactants and at the other electrode generates a high concentration of products, both of which increase the loss of voltage across the electrodes. The output voltage generated by a fuel cell can be expressed by equation 14.7. The ohmic system normalized by the active cell area is the area-specific resistance. The area-specific resistance is a function of the cell design, material choice, manufacturing technique, and because material properties change with temperature, operating conditions. The area-specific resistance is a key performance parameter, especially in high-temperature fuel cells, where the ohmic losses often dominate the overall polarization of the cell. Given a certain cell design and operating temperature, the bulk material contributions to ASR can also be calculated. Based on the detailed cell geometry, the lengths of both the ionic and electronic current passes and cross-sectional areas for current conduction can be measured. Together with the resistivities of the materials used, they yield the bulk ASR. The contact resistance cannot be calculated from fundamental data and is usually determined by difference between the measured total resistance and the computed bulk resistance. When using literature data for ASR, it is critical to verify the definition of ASR. Some researchers have defined ASRs to include the activation and concentration polarization as well as the ohmic polarization. Two examples of equation 14.7 are shown here, where for the PEMFC seal, activation losses are high due to the low temperature and ohmic losses tend to be low. Just the opposite is the case for the high temperature SOFC cell. As the current density increases toward the limit, the voltage drops sharply in both cases, and if the power per unit area were shown, it would have a maximum in the middle range of current density. This result resembles that of a heat engine with heat exchangers of a given size. As the power output is increased, the higher heat transfer requires a larger temperature difference, which in turn lowers the temperature difference across the heat engine and causes it to operate with lower efficiency. Okay, that's all for this task. Thank you very much, and see you next time.